research ideas on the data plane. And we've got 4 speakers. I will skip detailed bios. Our first speaker is from Huawei, Aytac. And we've got our second is from CMU, a grad student at CMU, Hun. Hun, raise your hand. There you go. And third is Praveen, another grad student from Edinburgh. And we'll close with Tim Stamler right there from Texas. So, without further ado,
Okay, good afternoon. So my name is Azgin, and today I'm going to talk about a project that we are working on, Stateless Forwarding in Information-Centric Networks. And we just started this project, and hopefully we are going to have something to demonstrate the next time we present. So first, I want to give a brief summary of the information-centric networking. So information-centric networking aims to replace the current IP source-centric design with a content-centric one. In this architecture, content can be fetched from anywhere in the network, from any repository, cache, or content source. So location doesn't matter. And there are various solutions to implement information-centric network, and we mainly focus on the 2 leading approaches, content-centric networking and named data networking. So these architectures are based on a pool-based solution. So we have interest and data primitives. The user makes a request, which we refer to as interest, and that request fetches the data packet. And ICN provides additional features. For instance, it provides in-network caching with the use of content stores at each router. It has pending interest table, which provides stateful forwarding. And the security is integrated within the packets with the use of signatures. And these features also allow ICN, in general, CCNINDN, to support multicasting, multi-homing, and mobility inherently. So here we show how the packet forwarding works in CCNINDN. And on the left, we show the router architecture. So we have those 3 components, content store, pending interest table, and the forwarding information base. The packet structure is based on TLV, so we mainly have 2 different types of packets, interest and data. We can have more primitives on that. So it carries a TLV-based content name. It carries optional TLV headers. And we also show how the forwarding works from the perspective of the interest packet. So when the router receives the interest, what happens is it first checks its content store to see whether there's an existing content in its cache. If there is, it responds with a data packet. If it doesn't, it goes through the pending interest table to check whether there's an existing request for that content or not. If there is no match, then it needs to go through the FIP, performing the longest prefix matching, and find the outgoing interface for that request and inserts the new PIT entry. After that, it forwards the interest. So if there is an existing entry in the PIT, what happens is that if it is coming from a different interface, it updates the PIT entry and drops interest. If it is coming from the same interface, then it just drops interest. So CCNINDN by default uses stateful forwarding. So for that purpose, we have the pending interest table, and pending interest table stores the information on the received request. These are content name, information on the interfaces, incoming and outgoing. If it is implemented, nonces and timeout values. So here, stateful forwarding has multiple purposes. The first one is to aggregate incoming requests. So if we have interest for the same content, we can aggregate them at the router, so we only need to forward just 1 request. It can be used to suppress attacks at the network edge if it's targeting the same content name. And it also creates breadcrumbs for the data packets to follow, as CCNINDN uses a synchronized forwarding in both directions. But there are some problems with stateful forwarding, as been shown in the literature, aggregation is limited to the edges, and it's also shown to not fully prevent attacks. And additionally, it can introduce significant overhead, both in storage and processing. As we show in this figure, the x-axis shows the well-behavedness ratio for the network traffic, which means that if it is equal to 1, every interest fetches a data packet. If it is 0, none of the interests fetches a data packet. So at different line rates, we observed that it can create an enormous number of entries in the PID table, which requires gigabytes of storage for just the PID table. So that can actually create a bottleneck for information-centric networking. So if we account for that, then what remains is the breadcrumb advantage that it provides. As in CCNINDN, none of the requests carry information on the host that makes the request. It needs to use the entries within the pending interest table to find the requester. But this can also be replicated by using in-packet filters, which provides stateless forwarding. So in-packet filter is an optional hop-by-hop header, which is updated at each hop along the path. We have different approaches we can use for that. We can use a Bloom filter, which is a static field filter. So it's constant size, and bits are set at each hop until it's retrieved by the content source. But on the reverse path, no modification is possible. So it can trigger false positives, and it can contribute to the overhead. But it is simple, and it requires only lookup and forward operation. We can use a counting Bloom filter, which can address some of the problems with the Bloom filter. It's dynamic. It uses 2 hop-by-hop optional headers, a constant size Bloom filter, and a variable size counter field. This is an optimized encoded counter. So on reverse path, we can update, and we can remove the matching entries. But it introduces additional complexity as we need to update at each hop. We can also use a dynamic in-packet filter. This is like appending labels at each hop. So we can just remove the labels when the data packet is returned. So in our research, we compared the Bloom filter and counting Bloom filter. And at the top of the slide, we show the regular Bloom filter performance. As we vary the number of interfaces and the number of hops, we observe significant overhead as we need to transmit packets over non-requesting interfaces. And when we compared with the counting Bloom filter using different network topologies, we observe significant improvements by using counting Bloom filter. That includes the additional overhead for the counter field. So what changes with the stateless forwarding in the packet flow is when we receive the interest after content store check and FIP processing, we just need to find local filter based on this interface information, update the in-packet filter, and then forward the interest. For the data packet, after performing a match on the content store, we go through an interface mapping table, which determines whether there is an interface matching that local filter. If there is, then we need to update it and then forward the data packet. So stateful ICN forwarding is already implemented in P4. It assumes nested TLVs. So what happens here is that initially it tracks the headers, the lower layer headers, the TLV format it uses, the name, and the components, because in CCNINDN we have, it can be like URI, it can have multiple components. We need to use each of those to apply on the FIP. So what we do is after the parser, we use a counting table which counts the number of components. Then we input that on the hash name table to find the hashes on both the full name and the components. And then we go over the PID table to determine whether there's an existing entry or not. And if it's, for instance, data packet, we need to remove that entry and then forward the data packet. If it's an interest, then we need to go to the FIP table and update the FIP table, update the PID table after extracting the interface information. So as we can see, using a stateful forwarding with the PIT, we need to introduce additional complexities for the design. Also, the PIT entries are stored in the register, and this is because the entries in CCN and NDN needs to be stored up to 4 seconds. This is the default timeout period. So if it is not designed perfectly, we can overwrite the existing entries, and that can also create additional problems. So what changes with the stateless design is that here we show our architecture. So we need to extract the in-packet filter, and that's also something that we are going to be updating while processing. So we only need one filter table that's going to do the processing for us, if it is going to be removing or inserting new entries. So for us, the main metrics of interest are the storage and processing overheads. For stateful forwarding especially, what are the requirements on the PITs, and what are the processing overheads for each of those scenarios? And also, in ICN, forwarding performance is a critical performance measure, because the name introduces additional complexity, and looking on all those names, which can be 20 components long, this can prevent to achieve the line rate. So forwarding latency and forwarding performance is a critical performance measure. So we also need to, in our case, we need to also examine the impact of stateless and stateful forwarding on one another. So again, this is an ongoing project, but compared to P4, Netronome NFP allows us for more realistic implementations, as it can provide high parallelized processing capabilities, flexible storage options, and the integration of P4 and ST also gives better options for the design. So we are actually started working on this one using a Julia Intelligent Server Adapter, and we also have other testing scenarios that we want to use. For instance, label-based forwarding in ICN, which requires a forwarding label table and a forwarding label within the packet header. Also, flow-driven ICN forwarding, which requires flow tables and flow identifiers within the packet headers. So again, hopefully, we are going to have some results next time we present. Thank you.
Any questions?
Okay. Thank you.